Hello, in this video I will be demonstrating how to use GLAD in order to compare data between Galectin 3, Galectin 3C and Galectin 7. Galectin 3C is a truncated version of Galectin 3, so we expect it to behave similar in microarray binding patterns as Galectin 3. However, Galectin 7 is different from both of these proteins and it should show differential binding patterns on the microarray. This data is available at the CFG website, which is functionalglycomics.org, and it has been published previously in this paper, published by our lab in Glycobiology journal. So the first step to working with GLAD is we have to download the Excel files which are available from the CFG website. Now we've already used Excel to GLAD to convert these files into the correct GLAD format, which is shown here. And if you open the file, you can see that it is in the GLAD format with ID, name, RFU, standard deviation, CV, rank, and the name too. Now, if you want to know more, there is a video for how to convert the Excel data to GLAD on this page. And you can do that following the video instructions. So next, let's take a look at the overall GLAD workflow. We enter the data in the correct GLAD format, and then you can either visualize the data using bar charts individually and then select specific glycans to add to the selections, or you can add the entire data from the files directly into the selections. You can then manipulate the data in a number of ways, such as you can save and load the data, you can normalize the data, you can sort and even filter this data. After that, you can create different stage 2 visualizations, such as group bar charts, where you can compare the data, or heat maps, or calendar heat maps, force directed graphs, and correlation plots. So let's go ahead and open a new GLAD tool page. And what we can start doing is we can start putting in our data. So to start putting in our data, we click on the use your own data button, and then we go to browse, and then we go to the folder which has all our data, and then we select all our data and click on open. The GLAD tool prompts you if you want to add all the 6 files to the selection. Once we hit OK, the GLAD tool imports all the data for all of these samples into the selections. However, it randomly chooses the color. And so now we can go in and change these colors to our liking. So we'll change this to maybe a dark green, and we'll keep this one as blue, making it easy to differentiate between Galectins 3, 7 and 3C. Now we also do not like this order where we have Galectin 7 sandwiched between Galectin 3 and 3C. So we can click on the sort data and we can specify Galectin 3, Galectin 3C, and Galectin 7. And you say sort samples. And now if you check, it is in the correct order of our liking. That is Galectin 3, Galectin 3C, and Galectin 7. Now after this, we can save this selections so that we can resume analyzing from this point onwards. To do that, we click on the Save Load Selections button and click on the Save Selections button. And we will call this Collected Selections. And we save that as a single file. We still have the data loaded in. So we start by first normalizing the data to equalize all of the information between the arrays. Once we have done that, we can start going to the stage 2 visualizations. Now group bar charts are bar charts, and since the CFG array has 600 data points, if we produce a group bar chart with all the array data, it looks like a very complicated figure. Hence, what we will do is we will filter the data based on some query. Now in this case, because they are Galectins, we will filter them by the query which is shown here. And we will choose the AND option. So if we click on filter glycans by name, we say OK. And now if we do a group bar chart, it shows us only the glycans which we had chosen for our analysis. Now this is the group bar chart, wherein for each glycan it shows us the data for all the different samples. At any given point, you can pull out the glycan structure window and you can put your mouse over these in order to see the structure of the glycans. You can also display the error bars by clicking on the settings of the group bar chart and clicking on display error bars and clicking on the group bar chart button. So now you can see the error bars in the figure as well, and you can pan across the data. You can also save the figure as a SVG. So here we will save it as a SVG in the demo, and we'll call this bar chart.svg, and you can reopen it in either a browser or Adobe Illustrator or any software which can handle SVG files. Next, what we will do is we will produce a heat map. Now for the heat map, we can check the settings over here. We can choose different color themes and we can change these values as well. So we can set values which we would like as cutoffs for the different colors. And then if we click on heat map, it produces a heat map which shows the data in the heat map format. Once again, you can pull out the glycan structure window and you can mouse over at it on any of the tiles to see the structure of the glycan. You can also save the image of the heat map, and you can see it can open up. The calendar heat map, on the other hand, allows you to visualize a large number of glycans in the form of a calendar layout where each block represents a sample. So in order to see the large number of glycan, let's undo our filter and get back all our data. So by clicking on the undo button, we undid the filtration, and now we have all our data, which is almost I would say 3000 data points or more. Now if we click on the calendar heat map function, it produces the calendar heat map, and here each block is the data for this particular sample, and this block is the data for this particular sample. So you can clearly visually compare the data between all of these samples in an easy manner. Now GLAD is smart enough to know that if the glycans are matching or not. For example, if the glycans do not match, or they have some glycans missing, GLAD will accordingly align those glycans. So here in the case of galectin 7, this white tile and this white tile and this white tile are missing glycans. And on the other hand, you have some glycans towards the end of galectin 7, which were not there in the earlier galectin 3 experiments. And this is because on the CFG website, it shows that the galectin 3 and 3C data was collected on CFG version 5.0 type glycan microarray, whereas galectin 7 was collected on the CFG version 5.1. So next, we can the next visualization is the force graph. Now this is a more advanced visualization, and it allows you to see similarities and different overlapping binding partners in a very easy manner. So if we click on the force graph, it creates an immediate network graph as shown here. In this, the colored nodes represent each sample, and the gray nodes are all the glycans in the study. And so the links which are formed are based on the signal obtained on the microarray. So you can, as previously shown, you can pull out the glycan structure window, and if you mouse over on any of the glycan nodes, it will produce the structure of the glycan. You can also double click on specific glycans or specific samples to see all the glycans which it binds to. And this can be useful to determine common binding partners. Notice that this is also clustered the data in a very unique manner. And you can see that galectin 7 data for both 5 microgram as well as 2 microgram group together or cluster together, whereas the galectin 3C clusters together over here and the galectin 3 data clusters together over here. So it's fascinating that this tool is able to quickly tell you which are the pairs of proteins which are actually truly similar to each other. You can also save the image of this force graph by clicking on the Save SVG button in the top right. Also, you can highlight specific glycans. So if you go to the search and highlight glycans and you type in a query, say like few K, it will highlight whatever glycans which have few K within the name. So if we click on Go, it shows all the glycans which have few Ks in their structure. And you can undo this by just clearing this and clicking on Go. The next thing what we see, the next visualization what we see is the correlation map. So the correlation map, basically what it does is it will create a correlation graph of all the samples. So what it does is it calculates the Pearson R value, the correlation coefficient between the samples, and it produces a heat map where it ranges from -1 to +1. -1 indicates a negative correlation, 0 indicates no correlation, and 1 indicates a strong positive correlation. So here you can see that the correlation map helps you identify, clearly visualize the differences between galectin 7 as compared to galectin 3C. So galectin 7 has very low correlation, R of almost 0.065 against the galectin 3 and 3C, but against itself it has a very high correlation of 0.986. And if you click on any tile over here, it produces a scatter plot. Now under ideal conditions, when a sample is compared against itself, all the data points should lie on the diagonal for this scatter plot. But in the case of Galectin 7 compared to Galectin 3C, for example, you can see that there is hardly any correlation. Whereas the other samples, you can see that the correlation is much better. The other plot which is available now is the bland ointment plot. This allows you to see the outlier glycans which bind differently between the two samples selected in this heat map. So here in this case, the data is between Galectin 7, 5 microgram versus 2 microgram, and picks out the outlier data points over here. Once again, you can see this structure of these data points by just hovering your mouse over these points, making it very easy to visualize the glycans which are involved. The last visualization is something which we've just added recently. It's the bubble box plot. And this actually gives you some statistical comparisons to make between the different data sets. In the bubble box plot, you can see that each glycan is represented by the bubbles, and for all of these glycans, if you mouse over the glycan, it will highlight the reading for that specific glycan for all the rest of the samples. So you can actually compare which are the top binders against all the samples using this. You can also pull out the glycan structure window, and you can put your mouse over to check the structure of these glycans. If there are a lot of glycans clubbing up over here, you can use the jitter data points toggle to spread out these spots and create something like bubbles, and that's why the name bubble box plot. You can also spray the data points, wherein you are only spreading out the top binders and not spreading out the lower binding glycans, and therefore you can see the glycans more clearly. The bubble box plot also allows you to draw the box plot, which is shown here. Unfortunately for this, there's not a lot of distribution in the data, or you can even show the mean lines which are shown here. This is the mean and the standard deviation for these data. And what is clearly visible is that Galectin 3C binds the array with significantly lower signal as compared to Galectin 3 or Galectin 7. However, based on the previous analysis of both correlation plots and force graph, it could be that even though the binding is lower, the specificity is still maintained in that it resembles the binding pattern of Galectin 3 more than that of Galectin 7. Filtering the glycans based on specific filters should allow us to see more statistical differences between the groups of glycans within the sample as well. So to conclude, GLAD is a visual analytics tool, and it should help the user quickly decipher such observations from complex glycan array data. The ability to view the structures on the fly with its interactivity should make it easier for users to uncover unknown patterns previously missed. GLAD selections which we saved could also be used as supplementary material in manuscripts for array users. Thank you.